In this lecture, we will discuss the autocorrelation function and a cross correlation function and some related problems. And autocorrelation function, and very specifically, this autocorrelation function we will define for a random process or a random variable. And generally, autocorrelation function is actually used to find the match or similarity between two signals, or if you use autocorrelation, we will use the match or similarity between a signal and its delayed version. Okay, but in case of random process, the autocorrelation function x of t is actually the expectation of the product of two random variable x of not x of t1 and x of t2. Okay, the same function at time t1 and t2 we are evaluating. Okay, so we can define this autocorrelation function Rx of t1 comma t2 because we are evaluating at two different instant. So this is simply defined as the expectation of random variables or at t is equal to t1 and t is equal to t2. So there is a random process and we are evaluating this function at t1 and t2. Okay, and we will find the expected value of x of t1 into x of t2. So mathematically, you can write this particular equation, integral minus infinity to infinity, again minus infinity to double integral x1, x2, and join probability density function of x1 comma x2. Okay, so this is the autocorrelation function, and if the process is a wide sense stationary process, or it depends only on the stationary process. For example, this is strictly a stationary process, a strictly stationary process, then it depends only on the difference between T2 and T1. So if it is a strict stationary process, it depends only, or the autocorrelation function only depends on the difference and not T1 and T2. So this T1 difference is, we will indicate T2 minus T1. So that's why this autocorrelation function can be written as Rx T2 minus T1 for all T1 and T2. Okay. Sometimes in this T2 minus T1, we will also indicate it as tau. So we can simply write this is Rx of tau. It depends only on the delay, that is tau. And now we can discuss some properties of this autocorrelation function. So if it's a wide sense stationary process or a stationary process, we can define this autocorrelation function like this. So this is assume that this is a stationary process. Okay, so it depends only on the time delay. So we know that if it is only depends on the delay, this time t1 and t2, and assume that t2 minus t1 is 2. That's a delay. So we can consider this simply 2 instant of time by taking the delay. Okay, so we will take one instant and the t plus 2 as the another instant of time, and we will take the expected value of these two. So we can define autocorrelation like this for a stationary process. Then if you substitute, so this is the first property, you can indicate that in this particular equation, if you substitute tau is equal to 0, so your equation becomes expected value of x of t plus 0 into x of t. So So that you can write expected value of x square of t. So this is Rx of 0, or we can say that this is a mean square value of the random variable or random process. Okay. So x square, expected value of x square of t is the mean square value. Okay. This is one property. And another property, the autocorrelation function is an even function. So that's why we can write Rx of tau and Rx of minus tau are equal. Okay. If it is an even function, we can also define this Rx of tau like this as expected value of x of t or expected value of x of t minus tau. So either you can use this relation x of t plus tau into x of t or x of t into x of t minus tau. Okay, because this is an even function. And third property, the maximum magnitude we will obtain at tau is equal to 0. Okay, so if you consider any random variable and the autocorrelation function is defined as Rx of tau is expected value of x of t plus tau into x of t. Okay, and when tau is equal to 0, you will get expected value of x square of t, and this value will be the maximum value. So we can indicate Rx of 0 will be the maximum value, because match also occurs when the delay of, if you consider any waveform, for example, this is a waveform, it checks from 0 to 1, and this is another waveform, or the same waveform, it's a delayed version. Okay, assume that it's from 2 to 3. And if you observe these two signal, for example, I'll explain the time domain, so x of t minus 1. Okay, it's a delayed version. So if you compare the match or similarity between, you can see that match is only up to this much. Okay, but if the delay of the signal is 0, there is another signal which the delay is 0, means the match will be maximum. If you compare the first and third waveform, the similarity is maximum. So that's why the autocorrelation function is maximum at tau is equal to 0, and all other values will be less than that. Okay, less than or equal to that. Okay, this is the autocorrelation properties. Now we'll discuss one problem. So here, the sinusoidal signal x of t, or a random process is defined as x of t is equal to a cos 2 pi fct plus theta. Assume that theta is a random variable that is uniformly distributed over the interval minus pi to pi. Find the autocorrelation function. So here, theta, the random variable, is indicated as uniformly distributed. So we need to write the general expression of uniform distribution. Okay, so if variable x is uniformly distributed between a and b, we can define that function like this, a probability density function. We can uniform distribution, we can write like this, that is, it's from a to b. Okay, and the amplitude will be 1 by b minus a. So similarly, if you write the uniform distribution function for this theta from minus pi to pi, you can write the probability density function like this. F of x will be 1 by 2 pi, okay, just like b minus a, from minus pi less than theta less than pi, and 0 otherwise. So in some questions, they will not directly give you the uniform distribution or the distribution of the function. They will indicate that as a standard. So uniform distribution is a standard distribution, and you can use this particular relation or general formula. From that, you can write the probability density function. Here, theta is uniformly distributed. So from minus pi to pi, it's uniformly distributed. So the amplitude of this becomes pi minus pi. Okay, this is f theta of theta. Okay, so we got the uniform distribution equation. Now we can find the autocorrelation function. So autocorrelation function is defined as Rx of tau is equal to expected value of x of t plus tau into x of tau. Okay, sorry, x of t, and in this particular x of t is given a cos 2 pi fct plus theta. So you can substitute here. It becomes the expected value of a cos 2 pi fct plus tau plus theta. Okay, this will be the one term, and another term it's a cos 2 pi fct plus theta. This is another term. So if you simplify this, it becomes a square cos 2 pi fct plus 2 pi fc tau plus theta. And second term is cos 2 pi fct plus theta. So you can see that this is cos A cos B, and if you expand cos A cos B, you can, this is A and this is B, so you can write it's 1 by 2 cos A plus B plus cos A minus B. So by using this trigonometry function, if you expand the previous term, it becomes anyway, this a square is a constant, so you can take outside, and there will be 1 by 2 if you expand, so you can write 1 by 2 outside. So remaining terms will be expected value of cos and A plus B. So we will get 4 pi fct plus 2 pi fc tau plus theta, the first term, and the second term will be cos 2 pi fc tau. Okay, this is second term, and in this particular case, theta is the random variable and it is uniformly distributed. So if you observe the terms, the second term does not contain any theta type. So we can consider this as a constant term, and it is independent of theta. So that's why we are considering it as a constant term. But in the first term, there is a theta. And if you find the expected value of the signal, or if you define the expected value of any signal x of t, you can write integral minus infinity to infinity x f of x dx. This is a general equation for finding the expected value. So we can apply, and also there's a rule, if x plus y, we can apply expected value of x plus expected value of y. And similarly, if there is a constant, if a is a constant, then it's simply that constant. And if there is a term like this, constant, a is a constant and x is a random variable, you can write a expected value of x. Okay, so by applying the properties of this mean, can evaluate the previous relation. So a square by 2, and the second term is integral minus infinity to infinity. It's 1 by 2 pi, because the probability density function is 1 by 2 pi, or you can say that it's from minus pi to pi. Okay, minus pi to pi cos 4 pi fct plus 2 pi fct, sorry, 2 pi fc tau plus theta and d theta. And the second term is actually a constant term, so we can simply write it's a square by 2 cos 2 pi fc tau. And if you look at this particular term, this is a sinusoidal waveform, and we are integrating its over a period minus pi to pi. So if you find the area of a cosine waveform or a sinusoidal waveform over a period, okay, so the average value or the mean value of the signal is 0. So if you integrate this, you will get 0. So at final expression Rx of tau, you will get only a simple term. It's a square by 2 cos 2 pi fc tau. So this is the autocorrelation function of the given random process. Okay. So if you plot the waveform, it will be like this. It's a cosine waveform. Okay, it's a cosine waveform. It's a cosine waveform, and the amplitude of the signal is a square by 2, and this is Rx of tau, and this is with respect to tau. Okay, and this duration we can indicate as 1 by fc. Okay, this is the time duration. So for this particular signal x of t, a cos 2 pi fct plus theta, you can see the final equation again a periodic function. Okay. Now we'll discuss the cross correlation. In general case, this is again the cross correlation function for a random process. In general case, cross correlation is correlation we will define actually the match or similarity between two signals x and y. Okay, so this is a general case, but here in the case of random process, the cross correlation function of x of t and y of t, okay, so is defined as rx of rxy tu. It's actually two instant of time. Either you can put a t and u, or you can put a t1 and t2. So at two different instant. Okay, if there is a signal like this for x of t random process, another random process which y of t, okay, and we need to find the autocorrelation function, sorry, cross correlation function of two signals. When it is a cross correlation, there will be two signals, x and y. If it is autocorrelation, both signals will be same. Here it is x and y. In the previous case, it's both signals are x and it's a delayed version. So we will evaluate two different instants. Either you can write t1 and t2, or you can put another two time instant t and u. Okay, this is the expected value of x of t and y of u. Or if you write the cross correlation function of yx, then the equation will be like this: y of t x of u. Okay, and it's a usual practice that cross correlation function, this t and u are two instants of time. Okay, either you can put t and u. In some textbook they will use t1 and t2 also. So we will also represent this correlation function as a correlation matrix. Okay, so two random process x of t and y of t may be conveniently displayed as in a matrix form. So r of tu, we can write rx tu. Okay, and that's a autocorrelation function of rx, and rxy is the cross correlation function, and ry x tu and ry tu. Okay, and we can consider one more special case. If x and y of are jointly stationary, okay, then this function you can write in terms of tau, where tau is defined as the difference between t and u. Okay, If the function is stationary or while it's in stationary process, then you can write r of tau in a simple tense, rx of tau, rxy of tau, ryx tau, and this is ry, not rx, ry of tau. Okay. Now we'll discuss some properties of cross correlation. So in the case of autocorrelation function, in case of autocorrelation function, this r of tau and r of minor tau are equal. So we can say that is an even function, but here it is not an even function. And another point, in the case of autocorrelation function, rx of 0 will give the maximum. But here we cannot say that at tau is equal to 0, we will get the maximum value, because we are evaluating two different signals. So it does not have its maximum at its origin. Okay. And it obeys another symmetric relation, that is rxy tau is equal to ryx minus tau. Okay, this is the one equality that you can use in the case of cross correlation. So this is a symmetry follows in cross correlation. And now we'll discuss one problem. So related to cross correlation function. Consider a set of quadrature modulated process x1 of t and x2 of t. That's two random processes are given. x1 of t is x of t into cos 2 pi f ct plus theta, and x2 of t is x of t sine 2 pi f ct plus theta, where fc is a carrier and theta is a random variable. So theta is the random variable, and it is uniformly distributed over 0 to 2 pi. Find the cross correlation. So again, it is given that is uniformly distributed. If it is uniformly distributed means we need to write the probability density function, because it's a standard case. So here theta is the variable, and you can see that it's uniformly distributed between 0 and 2 pi, and it is uniformly distributed means it's constant from 0 to 2 pi. And we know that the total area of this probability density function is equal to 1. So definitely if the width is 2 pi, height should be 1 by 2 pi, that 2 pi minus 0. Okay, so this is a probability density function here. So you can write it's 1 by 2 pi from 0 less than theta less than 2 pi and 0 otherwise. So the probability density function we can write like this if it is a uniformly distributed. So that's meaning it's a standard distribution, and now we need to find the cross correlation. So there are two signals r1 x1 of t and x2 of t. So we can write r12 of tau can be written as expected value of x1 of t and x2 of t minus tau. So either you can write t plus 2 and t, or you can write t minus 2. So anyway, we need two time instant. That's why we are put t and t minus 2. Or you can write t and u, then there will be two variables. So instead of that, we are writing t and t minus u. Okay. Or you can put t plus tau and t also. Okay. If you substitute this variables in the random process, it becomes so here if you substitute, it becomes x of t cos 2 pi fct plus theta, and the second term is x of t minus 2 sine 2 pi fc. It's actually t minus 2 plus theta. So now, if you write, if you group the terms, it becomes expected value of x of t and x of t minus 2. And the second term is cos 2 pi fct plus theta and sine 2 pi fct minus 2 pi fc2 plus theta. Okay. So we'll get different terms. Now we can see that this is cos A sine B. So we can expand this cos A sine B like this, 1 by 2 sine A plus B minus sine A minus B. Okay. So if you expand the previous term, it becomes expected value of x of t into x of t minus 2, and the second term is 1 by 2. It becomes sine 4 pi fct minus 2 pi fct plus 2 theta. Okay, this will be one term. Another term will be minus sine 2 pi fc tau. Okay. So now we can apply the expected value. So it becomes 1 by 2 is a constant, and remaining term you can write expected value of x of t into x of t minus 2 as a one term, and another term expected value of sine 4 pi fc t minus 2 pi fc tau. Okay. Then there also it's tau plus 2 theta minus sine 2 pi fc tau. Okay. And if you observe this particular term, the first term expected value of x of t and x of t minus tau, we can put as an autocorrelation function rx of tau. It's simply the expected value of x of t into x of t minus tau. Okay, so instead of that you can write like, and if you apply the expected value in the second term, there is actually two terms. If you consider the first term, it's actually a sinusoidal term, and the variable is random variable is theta. So if we evaluate the sinusoidal signal, because the expected value of variable can be written as x f of x dx. So if we integrate over a period, in this particular case, it's from 0 to 2 pi. If you integrate, it's 1 by 2 pi, and it's actually a sine term, and the variable is theta. So if you integrate over a period, you will get 0. Okay, so this term becomes 0 if you find the expected value, and there will be all one term, that's the second term, and the constant term, because here theta is the random variable, so tau we can consider as a constant. So expected value of sine 2 pi fc tau, it's simply sine 2 pi fc tau, because tau is a constant in this particular case. So we can write the final equation R12 of tau can be written as Rx of tau. That's equation for the first term. Okay, and the second term expected value is 0, and for the second term it's simply sine 2 pi fc tau, and there is a minus also. So you can write minus, and already there is a 1 by 2. So minus 1 by 2 Rx of sine 2 pi fc tau. And this is the final cross correlation function for the given question. And one more point we can add, if tau is equal to 0, in this particular equation, this sine terms become 0. So you can write R12 tau is equal to 0. And we can say that expected value of x1 of t and x2 of t. Okay, this becomes 0. Means we can say that two random process x1 of t and x2 of t are orthogonal to each other. So in this particular equation, if you substitute tau is equal to 0, and we will get the cross correlation function is equal to 0. That indicate that these two functions are orthogonal. Okay. Now we'll discuss one more concept, that's power spectral density, that we will discuss in the next class.